Okay, good morning, everyone. We are about to start this first seminar of the year. Today, we welcome Andrés Moya to give the first seminar, and I'm going to let Savita present him to you.
Good morning, everyone. I'm very happy to introduce Andy, which we were just discussing. I think we met like almost 20 years ago when I was doing my PhD. So anyway, so it's very nice to have you here. So Andy is a senior lecturer at the University of Valencia. He obtained his PhD in 2003 in Granada at the IAE. And he then had several postdoctoral positions at the Observatoire de Paris, the CAB, the University of Birmingham with the Marie Curie Fellowship. His main research interests are on stellar structure and evolution, exoplanet characterization, and special focus on asteroseismology and using machine learning AI tools for stellar characterization. And he is also, if you didn't say it, but you're also involved in Plato, doing all the specifications for one part of the pipeline. And he's now currently the Spanish PI of the HAYDN mission that he will present here. So,
thank you, Savita. Thank you and thanks for the opportunity of presenting you all this project. Today I'm going to talk about HAYDN. That is a project now. It's a proposal that is one of the now in the way of just proposed to be the next M8 ESA M8 mission. Now we are in the selection process, so it's now a project. But okay, we are really excited with this idea and project, and we are willing to push it as much as possible. HAYDN is the acronym of High Precision Asteroseismology in Dense Stellar Field. More or less, that's a spoiler of what we are going to do and what I'm going to present here. What I'm going to talk is about, in general, stars. The idea is that stars are the building blocks of almost all the cosmos. So it's the building blocks of the galaxies, and for studying galaxies, researchers use stellar characteristics many times, and also is the main object in exoplanetary system. And we need to understand the stars for understanding the exoplanets and also the stars themselves. So it's at the center of many research branches in astrophysics. So the idea of HAYDN and the idea of focusing in stellar physics is because stellar physics is the root of many other branches. For example, exoplanets. We need mass, radius, age, chemical composition of the stars for better understanding what is happening with these planets. Gravitational waves. We need to characterize properly the end of the life of a star as a progenitor of a gravitational wave. Nucleosynthesis, of course, the internal conditions and evolution of the stars. We need to characterize it as better as possible. Cosmology, we need distances, we need ages. Distances use stars somehow in different configurations. The stellar population, of course, but this is about the stars. And galactic archaeology is all about the stars: ages, surface, chemical composition, movement, clusters, etc. So stars are at the center of all these things. And not only knowing main characteristics like mass, radius, and ages, or luminosity. It's also about physics, angular momentum transport, chemical mixing. All this we need to understand all this for a better understanding of all these things. So this is the idea of HAYDN, to increase our knowledge of how stars work. What have we done in the past? In the past, we have used the spectroscopy, photometry, isochrones, position in the chart diagram. And with that, we have obtained masses and radius with typical uncertainty, precision. And this here of 10, 20%, and age 30, 50. There are other particular situations, but in general, this is what we have obtained. So low precision, low accuracy. It has a negative impact on the physics we derive with these stars and these characteristics. But recently, now we have added a new technique. Well, it's not that new, but now we have developed this technique a lot. We added to this list asteroseismology that I'm going to explain a little bit more in detail what it's about. And with it, with asteroseismology plus the previous things, we have increased it, improved our precision down to around 5% in mass and radius, around 10, 15% in age. So we have now a high precision, but we don't know anything about accuracy because there is a lot of physics there that there is a no. So we have increased the quality of the impact in the physics derived, but it's not enough in many cases. It's good precision, but we don't know anything about this more. So let me focus a little bit on asteroseismology because HAYDN, one of the things that HAYDN does is to include asteroseismology as a tool, as a technique for obtaining results in different branches. So it's not a goal itself, asteroseismology, is a technique that we use. So let me introduce a little bit about, just 3 slides about it. What is asteroseismology? You have a star. If you have any perturbation of the star, this perturbation just drive inside the star. That's a wave. This perturbation driving by the different parts of the internal structure of the star finally has a reflect on the surface. These surface effects and movements can be observed with radial velocity or light curves. We usually work with light curves. So if we have a light curve of a star like this, we have a lot of information about the star. So I love this sentence because what some people know is other people information. So for many people, this is noise. For us, it's a huge amount of information, and we love it. And if you do go to the Fourier domain, you do the Fourier transform of this, we have a lot of information. We have information about rotation and spots. We have information about granulation. And this small thing here is also information. These are pulsations in a solar light. This is a particular case, but it's okay for us. So the information, this power excess here has a lot of information about how the stars live. In asteroseismology, we treat the star as a sort of a resonant box with harmonics and nodes. And this is what we study to try to infer what is the internal structure and main characteristic of the star. This is the key goal. So if we go into this power excess, this is a real but very nice case. We can see a lot of frequencies, very clear, and with two patterns. There is a large, what we call large separation. There is the distance between just jumping one in the middle, so this with this or this with this. Large separation and small separations, the distance between two very close frequencies. And these two quantities are a direct measurement of this evolutionary stage of the star and the mean density. These are key for going into the modeling of the star. But also if we model the individual frequencies, we get a lot of information. Okay, with all this, for example, if we put together the Fourier transform of stars along a evolutionary track, we see that this power excess change in frequency and also in power. So the stellar structure and also the width, the position. So the stellar structure and the evolution is there. We can see how the star evolves just measuring these kind of things. So using asteroseismology, we have additional observables, additional information for models, not only the position, the chart diagram, and the metallicity. This is the idea. We add more information, and then the modeling can be can be do better and more precise. So this is the small introduction about asteroseismology. So as I have said previously, our understanding of stellar structure and evolution underpins most astrophysics, different branches. But high precision test for the models has been limited. This is the past, until what we can call a space photometry revolution. So space missions obtaining long light curves, Corot, Kepler tests. And thanks to them, we have learned a lot. And now we are able to do many things with asteroseismology. We have learned, now we have in global with this detecting resonance, the resonant oscillation of 10,000 of stars in the Milky Way. We've been able to understand and learn a lot of things about the stars now. And now we are prepared for the next step. Okay. With all this, we can also not only characterize the star, but also go into the stellar physics, into all the things that are inside the models, all the physics, chemical composition gradients, density stratification, internal rotation profile, et cetera. So now stellar interiors are accessible for us, thanks to asteroseismology. There was a old sentence of Eddington 100 years ago, saying that he thought that the only place completely inaccessible for human being was the interior of stars. No. The answer now, we know that it's no. We can do asteroseismology and understand how is the internal structure of the stars. Okay. But tests, that's the important point, tests are limited by the heterogeneity of field stars. All these missions have observed field stars. So with a huge range and unknown values of masses, ages, metallicities. So the parameter space is still large. The free parameter space is still large. And the physics that we don't know or poorly know or more or less know but not very good is a lot. All this is into the star. Equation of state, opacity, atmosphere, differential rotation, angular momentum transport, chemical mixing, convection in 1D, wow. Initial abundances, primordial helium, magnetic field, nucleosynthesis, blah, 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 blah. All this is inside the models. And many of these things are poorly known or like in convection that done with a 1D free parameter. That's it. So this precision we have now achieved is not enough and prevents reaching high accuracy. The unknown of all this, the fact that we don't fully understand the real physics inside the stars prevents reaching accuracy. And that's the point. HAYDN is proposed for doing this movement, this jump. HAYDN is from precision to accuracy. We propose to understand the physics, what is inside the stars, and then we can claim for accuracy. And these new generation models that we can do with HAYDN, with the data of HAYDN, can be used in other branches, just claiming for accuracy. That's we now physics is entering in an era of large surveys. We all know most of them. In space, Gaia, James Webb, Euclid, Roman, Plato, blah, blah. On ground, LSST, the spectroscopy survey, there are some of them, ELT, Einstein. All these promise to transform our understanding, but this potential, we only fulfill it if we accurately understand the stars. Okay? And this step depends on our ability to model these stars. So, what is the proposal of HAYDN for moving from precision to accuracy? mix control environments and asteroseismology. So doing asteroseismology in control environments, dense fields. For example, clusters. Doing asteroseismology in clusters. Globular cluster, open clusters. Not only in cluster, I will show, but more or less this is the idea. Because then we will have the internal structures of hundreds or even thousands stars co-evaluate. So we fix ages, more or less, chemical composition, less distances. And if you fix this, if you set this to given values for thousands of stars, then you can go into the physics. As soon as you have asteroseismology, all the frequencies, then you can understand and learn a lot about the physics. That is what we want to do. Kepler and TESS showed that the power of asteroseismology, but avoided crowded regions because of the field of view per pixel. I will go back to this. Plato also is devoted to field stars, bright, close stars, also heterogeneous in terms of ages, chemical composition, and distances. So with this in mind, HAYDN has 4 main scientific objectives. The first one is related with stellar physics directly, from all these low mass stars to massive stars, covering all the range. That these massive stars serve as progenitors of gravitational wave sources. A second one with stellar cluster evolution, understanding stellar class evolution and formation. It's anchoring a stellar H scale to percent level. That is key for many other branches, this H scale. Galactic archaeology, the history of the Milky Way and also dwarf galaxies, and exoplanets, to investigate the occurrence of and characteristics of exoplanets in these environments that are not the best one for exoplanets, but no one has taken a deep look to exoplanets in these environments. So, as I mentioned it has impact in many other branches, in many other physics. And stellar population, fundamental physics, multiple population in globular cluster, galactic evolution, binary stars, stellar nucleosynthesis, cosmic age and distance, scales, supernova progenitors, has impact in many different places. And for that, we propose 6 targets, to observe 6 targets. 47 TAC, that is our golden target, and observe it for 18 months. M67, HNG Perseus, it's a double cluster, Omega Cen, globular cluster, or the bulk of a small galaxy, we don't know. But this window to look at the intended bulk of our Milky Way, and AGC 6397, but different months of observation. And here comes the most complex table. Sorry for this, but it's quite informative. It's the only overwhelming thing. But here we can see, okay, this is all the scientific cases, the scientific objectives. Forget all this. Okay, this is the 6 fields we are going to observe. It has impacts in many of the things, but important for understand is this thing, is this part. M67 is a cluster of the age and metallicity of the sun, so it's full of solar twins. It's very interesting for us. 47 TAC is a globular cluster, old, low metallicity. HNC Perseus is a young, is a double young cluster full with many massive stars, very interesting for people doing massive stars. This is what we call the high precision sample. We will be there for a long time in order to obtain individual frequencies and then going into the real details of physics. And then the survey sample. the objects with many stars, like Omega Cent of the order of 20,000 stars, or Bade's window, 100,000 stars, or this globular, very low metallicity globular cluster, very old too. Very interesting. So we have tens or hundreds of thousands of stars in our sample at different targets. And this is derived into requirements. So physics, we are leaving physics now and entering into technique and the telescope and all these things. So the observational concept, as you may into it, is high precision, long, nearly uninterrupted photometric monitoring of the visible band, like Kepler, like Plato, like all them. We don't need to change this. So it's in the visible, the noise level is 13 ppm, visual magnitude around 9, or 300 for a magnitude around 15, 16. This is the point. The PSF that is linked to the field of view per pixel is a 1.3 arc seconds. Sampling time of 1 minute or 8 minutes. Continuous observation from 3 to 18 months. And for that, we will use a single telescope with a primary of 1.2 meters. This is the okay, focal length, interaction time, blah, blah, all this. And the field of view will be 1 degree for covering the complete object. I will go into this one a little bit later on in this one. So why we have Kepler, we have Plato, why we need HAYDN? Because of the field of view per pixel, the PSF. This is 47 stack. It's one of our golden object. And this is the field of view per pixel of test. Impossible to do anything. But also Plato, Kepler are too big. And the contamination is huge. So we need a field of view per pixel of 1.3 arc seconds in order to resolve the individual sources. And this is the only thing we need different from the other missions. For example, the field of view per pixel of Corot is larger than this field. We cannot do anything with that. So this is the only technical change. And the consortium, the HAYDN consortium is composed by researchers of 11 countries in Europe, and also some collaborators outside Europe. And in Spain, 7 institutions: University of Valencia, Granada, Alicante, and Barcelona, ICE, Canary IEC, and IAA. There are researchers from all these institutions. The scientific board is led by Italy, with currently a co-PI of France, and according to the money that the different countries put on the table, there are one or two researchers in the consortium. In Spain, we have 2, Juan Carlos Suarez and me, in the board. And in terms of engineering, the PI is Italy, and the telescope is going to be constructed by Italy, except the baffle, Belgium. The focal plane, a joint effort between the UK and France. The thermal system, the focal plane is UK, the electronics of Spain, and the thermal control unit, if needed, that is something that is not for sure now, is going to be done here in the AC. The electronic units is mainly done in Spain, power supply unit and CPU, and the electronic box in Granada and Valencia. The performance in Belgium, and the science data center is a joint effort of all the countries. And the science consortium We have already done a workshop last summer in Bologna, and it's composed by more than 200 researchers all around Europe, including experts on many different branches, because there are many people interested on the data and the results we are going to obtain. Hydrodynamical simulations, single and multiple stars, cosmology, spectroscopy, asteroseismology, clusters, galaxy formation and evolution, galaxy, gravitational waves, so planets. So people expert on all these are already in the consortium. And the Spanish consortium, Spanish idea, so I'm going to talk about Spain. We have experts also in many of these fields: stellar physics, modeling, stellar evolution, asteroseismology, rotation, activity, magnetism, stellar population, clusters, exoplanets, massive stars. People from expert on all these are already in the team, and also the instrumental contribution. This is the CPU, power unit, and thermal stability. This is what we are going to do. The electronic box, thermal stability. The proposed satellite is Euclid. Think about Euclid. It's very similar. It's a single telescope, a buffer. It's not different from Euclid. The primary is similar. In this sense, has no many differences. The focal plane is below the primary, and the telescope will be a two reflection telescope, a primary and secondary, some lenses here to correct the focal distance in order to obtain this field of view per pixel. That is the point of all this. This is the field corrector. This is the key part compared with other missions in order to obtain this accuracy. The focal plane just here, below the primary. And we also have heritage. So it's a mission that is not really a risk, a technical risk. We have a lot of heritages. We have a lot of knowledge on how to do it. The only change is the field of view per pixel. Maybe, I don't know how many of you have know what was Eddington. 1 and 2, 3, 4. 5. Okay, Eddington was supposed to be the first ESA the M1 was even selected for that, but previous to the final acquisition, it was down selected. But all the studies were done. So there's a huge amount of information already done from Eddington and was our baseline. We started from many details coming from Eddington as a starting point. We have not reinvented the wheel. Now the values are different from this, but not much different. Now we have done the detailed studies, but our heritage was the initial studies of Eddington. Was a pity because Eddington was a sort of Kepler with the same idea for exoplanets, but it's supposed to be launched 5-6 years before Kepler. No, after Kepler. No, no, before Kepler. Before Kepler. And finally, we lose this opportunity. And also Plato, that has many of the institutions are going to repeat the same technology of Plato for hiding. So no risk here. I'm almost finished. So the history of HAYDN. So it was one of the proposals in the white book a few years ago. ESA white book years ago. And we presented the mission, the proposal to M7, starting from scratch in 3 months. 3 months. And we reached the phase 0 stage, just with 5 competitors there. But we conducted the CDF study at ESA. It's a huge advantage for us because this is a massive technical study of the mission. So the mission is completely understood by ESA, but we were not selected for phase 8. But in 24, ESA suggests us to resubmit it to M8. We did it. And now we are in the competition. At the end of March, we should present the documents for the step 2. So now we are in this part only with competing with other 9 missions. So, summary. HAYDN is a proposal for the next N8. It does high precision, long, nearly uninterrupted photometric in the visible band of dense stellar fields. The idea is moving in stellar physics from precision to accuracy for developing the next generation models. And with this accuracy, we know that there will be a huge impact on many different branches in astrophysics. Spain has a major scientific role and technical role. In fact, we are the 3rd largest community in HAYDN, Italy, France, and then Spain. So we have a major contribution. And this is my key final sentence. So we are still open to new collaborations, new ideas, people that think that they can do very good science with HAYDN and with the data of HAYDN. We are open, they are welcome. So please just contact us and you jump into the consortium, and we will be really happy to increase the number of scientific cases that can be impacted by the mission. Thank you.
Okay, any questions? Yeah.
Thank you, Andy, for a very nice presentation. I have a great doubt. I know N67 is a very important cluster. It was our target 35 years ago with the network of 4-meter telescope, as you know. It was the main objective of Eddington, actually. But now you have decided to move to a globular cluster, 47 Tucana, which is population 2, is densely populated, so you will have to deal with crowded fields. What kind of stars would you like to observe in that cluster, and who would you solve the problem of these densely populated fields?
Okay. Yeah, sorry. The idea of globular clusters is because they are old. So we can learn a lot about how was the evolution of the initial stars, the first stars. This is very interesting for the people studying galaxies at high redshift, that it goes into the past a lot. So these initial populations, these initial star, low metallicity star, are very useful for many other people. And the point is that in a globular cluster, almost all the stars are in the red giant branch. So we can do asteroseismology, very nice asteroseismology with them. So the stars still in the main sequence are really low massive stars. And we cannot do asteroseismology with them, but also solar-like stars in the main sequences, we will have a few tens. If we observe M67, we will have a few tens or 100, but having thousands or hundreds of red giants stars, we can now we know how to do asteroseismology very precise with them, and we can get a lot of information about the different populations, about the different birth events, about the chemical evolution, and so taking a look at a globular cluster provides a lot of information about the evolution of the stars, taking the advantage of the red giant branch.
Time frame of the observation, because if you want to do red giants, you would need to be in the same field for years or
18 months. 18 months. Yeah, 18. Yeah, 18 months. This is the simulation and the calculation have been done to ensure that we can resolve individual frequencies, especially the mixed modes, or also the individual frequencies in red giants that has a lower frequency, so you need more observations, but we can resolve it with 18 months. So this is why we're focusing mainly in 47 top. And for M67, we will be for 9 months. That is also enough for resolving individual frequencies also in solar like stars. This is why we need to observe less time in M67 than in 47 top.
Any more questions?
Thank you for a very nice talk and advertising asteroseismology as a tool. One question, how does HAYDN compare to Roman? Especially Roman has a bit similar science case for crowded fields. What's the plate scale and what is the unique selling point of HAYDN?
We are in close contact with US researchers and with Roman representative. And what we have found is that first, well, they use a different wavelength. It's not visible. So in this sense, it's complementary. And second, the sampling time. So they are not going to be for months in the same field with a sampling time of 1 minute. So they can resolve dense fields, but they are not suitable for the asteroseismology in these fields. So the observations of Roma will be complementary, will add more information that is useful, but we cannot do real asteroseismology. The asteroseismology we want to do with HAYDN we cannot be done with Roma.
Thanks for the talk. This may be a bit of a naughty question. How much of the science, of this science could be done by getting years of time with Plato after the main mission?
Plato is the I mean, the strategy I described is asteroseismology have potential. As first missions appears, a space mission, then we start learning that is a very nice tool and start learning how to use it. And now we are prepared to use it as a tool for other things, not to learn how to use asteroseismology itself and getting the details. Plato is the last one that will help us to finally understand how to extract the most of asteroseismology for this thing. Plato is not going to observe dense fields. Maybe the outer surrounding of a dense field, because the field of the pixel is quite big. Yeah, I can. So the field of view per pixel of Plato is impossible to resolve individual sources in dense fields. So it will be mainly focus on field stars. And this field stars has at least three parameters that makes very difficult to go into the details of the physics. If you don't know the age, in principle, you don't know the age. You don't know the chemical composition except with an uncertainty, and the distance, all with an uncertainty, but it's just one case here, another case different there, another case different there. So the experiments we can do for understanding the physics inside is less precise. There are different physics that fulfill these inputs, these observables. But if you have 100 of stars with the same, in the same case, then you need to go into the physics to fine tune all the things, doing the same thing together at the same time. So these dense fields are critical for this step, and Plato is unlikely to do it. He will provide a lot of field stars, and it will be great for fine-tuning our knowledge about how asteroseismology works and increase the precision. We are very good doing precise values now, and later will be better, even better. We will reach the promises are 10% in age and less than 5% in mass and radius, and we can do that in precision.
Okay. Yeah.
Thank you very much, Andy, for a very interesting overview on that mission. You showed that there are basically 6 main targets, right? Like 6 more or less clusters. So the mission duration is a few. I just added up the months, so it's 4 years. How many years is the?
Yes, it's 4 years.
Yeah. Is there? Yeah. Is there any ideas or are there thoughts of like secondary targets? For example, if one of them doesn't work out for whatever reason, or if there's an extended mission, or is there any idea what you can put the capabilities of HAYDN?
Yes.
Further?
Yes. We have 2 sets of possible targets, additional targets. This priority 0. We have a group of priority 1 and priority 2, but currently ESA doesn't ask for it. So in the current stage, ESA asks for the main mission and not extension. This will come in the phase in next steps. But now they are just asking for the main 4 year and a half mission, and what are you going to do with this? And we have prepared the more targets, more really interesting targets, globular cluster and young clusters.
Great, thank you.
Hey, will you have complementary information for all the targets will be observed? Because as far as I understand, without the temperature or even maybe radial velocities, you cannot say if it's a foreground, background, and you need the temperature as well. Otherwise, any data is useless.
Yes, fully agree. Yes.
So you will have from what?
And
for all the targets.
Yeah, but the point is that we have to think about the timeline of this. So now we are in the initial selection. If everything goes as planned, this M8 mission will be launched in 2041. So, of course, we have to move in the direction of showing that we need spectroscopy, ground-based spectroscopy for the targets. And now we are also in conversation with different future spectrographs that are now planned with different timelines. But the real one we are going to use is to come, but because it has been working in 41. But yes, don't remember the name of a spectrograph in ELT. It's a multi-fiber. We need a multi-object spectrograph, high-resolution spectrograph that can resolve dense fields. So it is now under development. It's a project. It's not there. But we know that there are plans to have it in time, and we are in contact with them because, of course, we need a spectroscopy for all the stars. We need. It's the additional. In fact. This is what I distances that or sending the same cluster, spectroscopy, and like all together with all the.
Okay, any more?
Quick question. Can you remind me of the orbit that is anticipated? The orbit.
It's a L2. L2. Huh? Yes. But it's still quite big. It's orbiting around L2. Yes, but many people is going there.
Okay, any more questions? If not, then we thank Andrés again for the nice talk. And thank you all for coming. See you next week in the next seminar. And the students, you all note down, except if there's any new student. So come here, please. Thank you.